So yesterday we were discussing some of the applications of ferrites. What I wanted to mention is that along with the technological applications, there are a lot of development of physics which happens. They essentially go parallel. See, many times because of the commercial need, you develop a material and slowly you try to understand that particular material. That's the way normally it happens. You discover something and then you try to understand and go along that particular thing. In principle, with the discovery, very old discovery of ferrites, there are a lot of things which could be understood. First of all, the concept of ferrimagnetism evolved from the ferrites, because it was the data of Geo, and where he was making those oxides and finding out the magnetic moments to be much smaller than what he would have expected, using which the idea came from to nail that they are antiferromagnetically coupled. So the concept of ferrimagnetism itself got developed because of the data which was available on the ferrite materials. Then the model development, Nail's model. What we call as a two sublattice model, assuming that all the magnetic moments on the A side are parallel, magnetic moments on all the B side are parallel, and between A and B they are anti-parallel. Then another thing is electrical transport, which is generally people think electrical transport essentially means only for metallic materials. Oh, sorry. Thank you. So generally believe that it's only for conductors that you are talking about electrical transport, but even in insulators it's very, very important, and I had given you example. Though they are all supposed to be insulators, but even within insulators, what is the resistivity becomes very, very important for ferrites. For example, if you are going for very high frequency applications, then you require materials which must have very, very large resistivity. So you must understand how actually the electrical conduction takes place in the ferrites, and basically it's the hopping model. This got developed as a result of preparing better materials with higher resistivity. Then high power effects. What happens when you subject the same material to very high power of microwaves? For example, as I had given you example last time, radars, it has to be emitted to some distances, and therefore the power that the material is going to face is going to be huge. Now the properties which we see at low power may not work for high power. In general, they do not work for high power. So you have to understand the high power effects, okay, and try to see that your material works also at the high power, okay, and how much you can push the material, whatever properties you have assumed at the low power, or you have got at the low power, okay, how it can be pushed to high power. To understand and to make it translate, you have to understand that particular material, especially you have to understand high power effects. And there have been a lot of work on high power effects. And there is a particular line width which you call as a delta HK. I will not explain these things too much, which is called spin wave line width, which essentially tells how at the high power the energy of the system goes to the lattice. And this relates to a subject which is called ferromagnetic relaxation. And people are still working on this particular thing. delta HK. See, when I'll be talking about FMR later in the afternoon, there is a line width when you do resonance measurement, okay, which we call as a delta H, which is FMR line width. So these are all microwave properties. There is something which is called delta H effective, okay, where you are off resonance and you are seeing the loss in the material. It's essentially reflecting the loss, okay, and delta HK is related to how the to the high power effects. Essentially, it tells you how the power is being transferred to the lattice. How the, I mean, for example, you're exciting the system with high power, okay, you're creating a spin system there. Now, eventually, the energy that you are pumping inside this particular thing have to go to the lattice, which means essentially the material will be heated up. Okay, essentially lattice means there will be atoms which will be vibrating more, okay, and when they are vibrating more, then it will get heated up. Essentially, what we are calling heating is just vibration of the atoms. All right. Now, how there is a link of this power which is going from the spin system to the lattice. This is what we call as a ferromagnetic relaxation, and delta HK is one of the reflections of that particular thing. So generally, you expect to have a better high power effect, delta HK should be large. Essentially, the lattice, the energy should go to the lattice faster. It should not remain in spin system too much. Okay. So these are the things, these are the areas which got developed as a result of ferrite development, which are essentially enriched physics to understand these things. And as I told, I mean, you can see even the papers today on ferromagnetic relaxation is not, well, there are a lot of things still to be understood and to be worked out. How actually the magnons, like you have phonons, you have magnons here, how the magnons are excited, how the energy actually gets transferred from the spin system, the magnetic system, to the lattice. So these were the contribution of this particular area as far as the fundamental physics is concerned. So whenever we are having technological development, see, that's what actually some of you were asking questions yesterday. It often happens, the industry people are always in hurry because, for them time is extremely important. Okay, if there are two industries who are competing, okay, it makes a lot of difference if you are the first one to produce a particular thing in the market or a particular device into the market. You have an edge over it. So for them, time is very, very important. And physics understanding takes certain amount of time. So many times they don't care for physics. They somehow work out so that the device works. Okay? And many times it's followed by understanding of physics. Of course, it happens the other way also, that you understand physics and then you predict something. That if I do this thing, device may work like that. Okay? But in many of the very, very active fields, what happens is just the opposite. People, somehow industry people manage, okay, this is the, I do this doping, the material is very good for high power. But why this particular material, why this is better, it takes a certain amount of time to understand it. All right? So this is what happens, and generally the physics understanding and technological development, they always happen parallel to each other. And remember, if you are working on a problem where there is a lot of interest of industry getting money for you, I mean, which is very, very important if you are doing experimental research, because all the equipments that we are talking yesterday, I was talking yesterday evening, they are fairly expensive, and if you want to develop that particular laboratory, there should be somebody who should be able to support you. Okay, government cannot support everything. Okay, so support has to come, and if it is of industrial interest, the industry will support you. When there are a lot of laboratories, not in the area of magnetism, not only in the area of magnetism, but in many multiple areas where big industries have set up labs in the universities just to do the research because they are interested in that particular topic. So they are supporting them. Now, there are one or two other topics which I want to discuss before I want to go to thin films, which is what I had planned for today morning lecture. One thing which I had sort of mentioned is the two sublattice model yesterday, where the net magnetic moment on the system mu is given by mu b minus mu a. Generally, the magnetic moment on the B side is higher than A, but it actually should be the modulus of the two. Sorry. Mu B minus mu A. All right. Now, I also mentioned that because of this difference, you do not get the entire magnetic moment which is available to you in the form of magnetic ions. Had they all been parallel, you would have got much better magnetic moment. But on the other hand, because of the antiferromagnetic coupling, the overall magnetic moment on a molecule, let's put it, or what we call as a formula unit, is smaller. Now, there is always interest for certain device applications to push this magnetization higher and higher. And for that, one possibility is that you make mu A smaller and smaller. So the difference becomes larger. And one of the things which has been often done is to dope your material or include the material with zinc 2 plus, which is a non-magnetic. And this has a preference to go to the A side. So what will happen, even if you do nothing to B side, if A side you are putting non-magnetic ions, mu A will come down. When mu A will come down, the net magnetic moment will go up. So that's why in many of these systems, in fact many of the examples which I had given you yesterday of various type of ferrites which are used for application, you will find zinc there. It is essential to enhance the magnetic moment. But remember, many times enhancement of magnetic moment may not be suitable for the resistivity applications. So it depends again on the frequency and what you really want, at what frequency you want your device to work. Okay. For example, garnet has a very low magnetization, that's what we discussed, but garnet has extremely high resistivity. So for microwave applications, many times people will prefer YIG, yttrium iron garnet. Okay. Even though they are working with much lower magnetization, but just because it has a higher resistivity. So again, depends on your frequency of interest, where you would like to, thank you sir, where you would like to work. Okay. Now let us suppose we keep on adding mu A. All right. Can we put all the ions on A side which are only zinc? Can I make mu A is equal to 0 and get magnetic moment largest? Unfortunately, it does not happen. The reason is that, remember, Nail's model worked by assuming that AB coupling is the strongest. Now, as you are putting non-magnetic ions on the A side, essentially the magnetic moment on A side goes down. So automatically the coupling will go down. See, for example, if there is no magnetic ion on the A side, with what B ions will couple to? There is no magnetic moment there. All right. Now, as we keep on adding more and more zinc, what will happen? This AB coupling will also get diluted. Now, once it keeps on getting diluted, then the magnetic moments which were being forced in B side, which were being forced to be together because of this strong AB coupling, they will start diverging. They will no longer be parallel. And this is what is called canting. I am trying to explain it in the most simple form. So there are theories of canting and how to calculate angles and things like that, but I am not going to that particular thing. So what you find that if you plot, in fact I will give you the actual plot in my tomorrow's class because I have worked on this particular problem quite a bit. So my tomorrow's lecture will be essentially based on this particular idea. So if you have a ferrite, you keep on adding zinc, you will find initially the magnetic moment will go up, and around 40 to 50% when A site is filled with zinc plus ions, 2 plus ions, it will start reducing. And for pure zinc ferrite, again it will become 0. Because there is no ion, magnetic ion on the A side, B side. Sorry, A side. Because if it's purely zinc ferrite, A side is completely filled with zinc ions. Then the only exchange interaction which is there is BB, which is antiferromagnetic in its own sense, And therefore, pure zinc ferrite is supposed to be non-magnetic or rather antiferromagnetic with a very low nail temperature. It has a nail temperature of 4 or 5 degrees Kelvin, I don't remember. Of course, I will not be able to tell you about that particular thing. There is a lot of interest because we have seen, in fact, in our own group, we have seen that if the same material, zinc ferrite, if you make in thin film form, nanocrystalline form, it becomes magnetic. Essentially, the idea is that in that case, the preference of zinc to the A side gets lost, and some of the zinc side ions also go on the B side. So we have seen that in our own group, we have seen, and there have been before that, Professor Narayan Swami's group in Chennai, they have shown on the powder, a very highly quoted paper of his, where they have shown in the powders that zinc ferrite becomes magnetic when the grain size, when the particle size becomes very small. So these preferential sites also change when you are making the material in the form of nanocrystalline materials. That's why there is a lot of interest in thin films and nanocrystalline materials. Okay, then a few words about hard ferromagnets. Hard. Before I go to thin films, I had mentioned to you about the application for permanent magnetic materials. I will just give you an example of 4 different types of materials which are used. First, probably one of the most traditional things are alnicomagnets. As the name suggests, it contains aluminum, nickel, and cobalt. That's why it's called alnicomagnets. Of course, it has iron also in it. It gives you a BH max of the order of 13 mega Gauss Oersted. It's a Gaussian system. But these are metallic. So if you want to use for some application where you are using high frequency, they are not very good. The second type is what we had called ferrites. I told you yesterday about strontium ferrite and barium ferrite. They have comparatively much lower BH max. So of the order of only 5 million giga Oersted. Not giga Oersted, Gauss Oersted, sorry. But as I told you last time again, this has the advantage of being very cheap, comparatively very cheap, and also these are insulators. So if you want to look for high frequency application, these are very commonly used. Then there are 2 other types of permanent magnets which I will talk, which are specialized permanent magnets. One is samarium cobalt. We have a BH max of the order of 35 Gauss Oersted. They are very, very expensive magnets. I haven't unfortunately not worked on any of these areas, permanent magnets, so I will not be able to give you what is the precise current status of these things. But I know that the 4th one, there is still a lot of work going on, which are niobium iron boron magnets. Which has, this is 64 they are much cheaper in comparison to samarium cobalt. They have much better BH max. Sometimes people use nitriding to put some nitrogen to help TC because the Curie temperature is also important. Problem here is the Curie temperature is somewhat smaller. So people tried it to make TC better. There are many compositions which are being tried, as I mentioned to you. I know there are some people even in IIT Bombay who have been working on these type of magnets, negative iron boron magnet. They have been still work going on this particular magnet to enhance this thing and make it a better material. So I am probably giving you some glimpse of these type of magnetic materials just to give you a feeling of how the field has evolved, at least during my lifetime, right from the time when I was a PhD student to the time when I retired as a person working in the magnetism. So these are the way the magnetism area developed. Somewhere, let's say around 1970s, it was realized that the crystalline order is not a must for a magnetic order. Let me explain what I mean by it. See, till that time, all the magnetic materials had proper crystal structure. But you know, the solids can also be amorphous. Whenever we used to give talk on amorphous material, we used to always quote the first sentence which Simon has written in his famous book, Physics of Solids, that it would have been impossible to understand the theory of solids had the ideal structure for every solid would not have been a perfect crystalline structure. The study of solid state physics has evolved or has been considered as a study of a crystalline structure. Your Bloch's law, band structure, they are all derived with a lattice in mind. We started when conventionally solid state physics, we had been starting with the study of crystals. Not necessarily these days. For example, if you look at a Schroft and Berman, it does not start with crystalline structure, but all Kittel and old timer books, they will always start with crystal structure, because that was supposed to be the starting point of solid state physics. You assume your solid to be crystalline. Okay, it can be polycrystalline, that's a different question. But on the other hand, at a small scale, you will always find atoms to be arranged in a regular fashion. And you can always characterize its crystal structure. It's not that people were not knowing amorphous materials. For example, the window glass that we have been using is known for a very long time, which is amorphous, in which there is no order. If you take X-ray, you will not get any peak. All right? But at that time, people sort of look down at them and say, oh, these are super cool liquids. Because in liquid, there is no order other than liquid crystals. So they call it super cool liquid. So they were never considered as a mainframe solid state physics. And just for your interest, probably you will all realize, I'm not sure if you are aware, so let me just make this statement, that the name of solid state physics got changed to condensed matter physics. Because what traditionally solid state physics were doing were only studying crystalline structures. And when you include the study of amorphous materials and materials like liquid crystals, which are crystalline but they are liquid, then the entire area was renamed, rechristianed as condensed matter physics. All right? Now, in amorphous semiconductors, there had been a lot of work. Suddenly, they found that amorphous semiconductors are wonderful material. And when you are to make amorphous material is comparatively easier. Now, the same thing started even in the area of magnetism. There was a famous paper of Gubanov, I forgot the name of, to write the name of the year in which it got published. It is a Russian paper, Gubanov. If I can do a Google search on this particular thing, I will add in my notes which year he published paper, in which he said that actually crystalline order is not must for magnetism. An amorphous material can also have crystalline order. And somewhere in 60s, late 60s or early 70s, I'm not very sure, the Paul Louage group in Caltech probably they were the first, developed an amorphous magnet. And entirely new development, a new area started getting developed, which we call as rapidly quenched materials. Rapidly quenched materials. So the idea there was that you have a material in liquid form. Liquid form, there is no order. You cool it suddenly, very, very rapidly. And what he used to do, that there was an induction furnace in which he has to liquefy this particular material, and there was a very fast moving wheel, copper wheel, and the material falls on that and immediately get liquefied, solidified, and the quenching rates were expected to be of the order of 10 to the power 6 K per second. So whatever was the liquid structure gets stabilized into solid form, and they found it to be magnetic. Traditionally I am talking now, many more type of amorphous ferromagnets have been developed. It was iron 80 boron 20 type of 80% transition metal, 20% what they used to call metalloid. The biggest advantage with them, though they are metallic, but because there is no crystalline order, their resistivity is very much higher. Typical resistivity of a conductor, do you know what is the idea of order of magnitude? Order of magnitude. Any one of you? What are the resistivity of a metal, typical metal, resistivity? They are typically of the order of 1 ohm centimeter. Sorry, 10 power minus 6 ohms, what I am talking, 10 power minus 6 ohm centimeter. Micro-ohm centimeter, it's of the order of 1 micro-ohm centimeter. It's a mixed unit, you are using centimeter here, while ohm is a Gaussian unit. Ohm is not a Gaussian unit, it is SI unit, centimeter is a Gaussian unit. And I have always wondered why people have been using ohm centimeter rather than ohm meter. And I thought the blame was to semiconductor people, because semiconductor people, all the resistivities are of the order of ohm centimeter. So rather than always trying to say that 10 to the power minus 2 ohm meter, they said 1 ohm centimeter. So I thought that was they were the culprit. All right. Now these are the materials who have resistivity of the order of 100 ohm centimeter, 100 micro ohm centimeter, micro ohm centimeter. Two orders of magnitude higher resistivities. For transformer, all they thought it's a wonderful material. See, for electricity distribution, you have transformers. Transformer, you always use a metallic core to couple. And even at 50 hertz, USA it's 60, here it's 50. Okay, it's fairly low frequency, but there's going to be eddy current loss. And you are remembering every time when you are transmitting power from your generator to across the world, okay, you are going to use transformer, and every time you are using transformer, you are going to lose certain amount of energy. All right. If you could increase the resistivity by 2 orders of magnitude, there will be huge saving in the power. And this particular area picked up like a fire. How are there problems? The problems were that if you are going to use in transformers, they are going to get heated up. After all, whatever it is, there will be some eddy current losses. And that particular loss will go eventually to the atoms. Atoms will start vibrating more, and eventually it becomes hot. And because these are sort of unstable, or what you want to call metastable state, you have rapidly quenched them. As you start heating them, they are slowly getting crystallized. Because that's not a really favorable state energetically for them. They are sort of put into some sort of potential well, and as you keep on giving them energy, they will start becoming crystalline. So the lifetime of that particular material was becoming not very large. Still, I am not sure what is the current status again. people realized that so long you are using small transformers where heating is not very large, metallic glasses were of use. And with metallic glass, a lot of study of amorphous magnetism started, even in thin film form. I gave you example about magnetic bubbles, which I'll be talking later, where also people started using amorphous materials. So this area of amorphous material was the most fashionable area somewhere in late 1970s to early 80s. Anybody in magnetism group, you will find worldwide people are working on some sort of amorphous material. Then people, in order to improve its thermal stability, because that was one of the concern for these things, people also started using material in which you purposely develop some crystallines. It's not 100% amorphous, but it has also some crystallites embedded in it. And that was considered a superior material. In fact, just before giving this talk, I did a Google search to find out what is the status of metallic glasses, because I was working on metallic glasses when I joined IIT Bombay for a long time, and slowly the fashion changed, and we also changed. We went to different areas, and I was not very sure of what happened to their applications. And I found that they are still commercially available and they are still being used. Allied Chemicals in USA was one of the major company who was working on this particular thing, and I found their quotations that if you want this much, what is the cost and things like that, and they have also given certain type of. So it's definitely being used at this moment. So it's not a sort of a complete tragic story like magnetic bubbles. It's being used. Probably people are not doing too much of research on the standard metallic glasses, but still there are still a large amount of amorphous materials which people are working on one form or the other, or materials in which some crystals are embedded on it. So now I think I have stopped. I will stop of what I want to talk about bulk materials, because see, the way I had categorized my talks was one on general basic magnetism, another bulk material, third on thin film material, and 3 talks which I want to do with PowerPoint. One was basically on giving various techniques, another on crystal structure, and third on ferromagnetic resonance, because that I wanted to treat little special because that's one of my favorite subject. And also it's a technique which has been used over ages with some modification or the other, and gives you a lot of very wonderful information. So, in fact, this talk I wanted to start with thin films, but because we had some leftover material, so I did with that. Okay, now let's come to magnetic thin films. Why do we at all work on thin films? Because every time you are going to the smaller and smaller size of devices, and therefore you would like to use a smaller and smaller amount of material to be used. Earlier computers were huge. Now computers are tiny. Your mobile phone is also a computer. It can do a lot of calculation. All right, what computers are doing, sizes are becoming small. If the sizes are being small, and then components cannot be large. Components also have to become smaller. And if the components have to become smaller, you cannot really use bulk materials. You have to go to thin films. That's the commercial need, that we have to go to thin films. All right. So obviously, following trend in every area like semiconductors, in magnetism people started working on thin film. So the first idea was miniaturization of devices. But then people realized that when you make the same material, I am talking specifically about magnetic materials now, in thin film form, the property turns out to be reasonably different or quite different from their bulk counterpart. Suppose I deposit a film of, let's say, magnetite, and measure its properties, many times quite different from what is the bulk property. So people started working more and more in thin films, because now essentially you have to restart your work, because in bulk very well, you do this doping, this is the property you will get. In this particular area was completely understood, so to say. But when you are making thin films, that property is not seen. So now you have to redevelop your physics or redevelop your technology. What type of doping I should do to get what I want. Of course, it opened new perspectives, okay, new possibilities, but nevertheless you found the magnetic properties are different, and therefore people started working on magnetic properties. And why they are different? One of the most important criteria is microstructure, about which I had talked. Microstructure, texture, these are things that you are. Also because there are grain boundaries. See, like between domains you have a domain wall, you have grain, crystalline material, and there is another grain. Now in between there is a grain boundary, okay, which neither belongs to this crystal nor belongs to that crystal. Okay, now this can also play havoc on your magnetic properties, because you know if it is properly crystalline, this is the property it will have. But, and remember, if I keep on making grain size smaller, for which there was a need, I had mentioned about it yesterday. If I want to make grain size smaller, I am always going to increase the grain boundary volume ratio. So I have to take care of that particular thing also. In fact, one of the things which often happens, which most of the time happens, that if you measure MH loop, in which you see very nice saturation, in thin films, it keeps on increasing. It does not show saturation. All right, because this poorly magnetized region which is there between grain boundaries, I mean, they are not, we are not sure whether we call them paramagnets, we are not very sure whether we call them super paramagnet, we are not sure whether we call them ferromagnet. They are having some sort of odd structure. And you keep on aligning magnetic moments there. In fact, that's the reason that you do not get even the 4 pi image that you got in the bulk, because there is significant amount of material which is in that poor state. In fact, my next talk tomorrow will start with this statement that whenever you are talking of thin films, you generally find magnetization to be significantly smaller than their bulk value because of this particular problem. All right. So these things, then there is also a possibility how you have made the material. Many of the thin film deposition methods actually use some sort of a quenching. Either you are doing sputtering, then you are essentially cooling from the gaseous state, or you are making laser ablation, then again you are ablating the sample and then depositing on your, so essentially some sort of a quenching, which can freeze in completely different type of, preferences towards the sites. So this becomes a totally different area, and enormous amount of interest started in the area of thin films. But if I look back myself now, and I start looking at what is the first thing that made a huge impact as far as magnetic thin films are concerned, from the point of view of technology and from the point of physics, is a very tragic story of magnetic bubbles. So let me spend some time, 10-15 minutes, about magnetic bubbles. Of course, these days many of the magnetism people would not have even heard of magnetic bubbles, because that's a story which is lost around 80s. It was lost between 70 to 80. That was a very, very important type of story. So what are magnetic bubbles? It's basically cylindrical domains. So you assume there is a thin film, and what I am showing you is the top surface of thin film, and it has a very large uniaxial anisotropy perpendicular to the film plane. Otherwise, the magnetic domains in this particular material would not like to point with a magnetization normal to film plane because of the magnetostatic energy that I had discussed earlier. They will always like to align themselves along the largest dimension. So if this is like this and this is thin film, most of the domains will have magnetic moment aligned in this particular direction, not along this direction. So you must build in an anisotropy, either crystalline anisotropy or any other anisotropy, so that your magnetic domains are pointing up and down and not along this particular direction. Now you try to magnetize, let's suppose in this particular direction. When you try to magnetize it, you will find the magnetic domains which are along the direction of the field, they will grow up, and which are opposite to that will reduce. Just before saturation, when the material becomes completely a single domain, you will find in a state where essentially all the materials, if certain properties are maintained of the material, if certain qualities are maintained, you will find the entire material has become a single domain, but there are still some tiny domains which have their magnetic moments aligned in a direction opposite. If you keep on increasing the field, they'll suddenly collapse and the entire material will become single domain. If you reduce the field, again they will appear. So if you look in microscope, it essentially looks like magnetic bubbles. If you have so bubbles, you see a bubble collapsing, bubble generating. So that's why they were called magnetic bubbles. And the idea came at that time that if you have magnetic bubble, presence of magnetic bubble can be called 1 and absence can be called 0, and this can be used as a recording device, as a recording media. And the size of these domains can be made very, very small from the point of view of that time, not from the time of today when we are talking of terabytes. Okay. And there was again very large interest on these things. Now, if you want to have these, let me just see whether I have missed any point. Yeah, another important part was that earlier, I mean even today, your hard disk uses a mechanical device. Okay, something rotates and comes near the head and then you are reading the information. Okay, the idea of magnetic bubbles is that there will be no mechanical device. The head will be built in there on the system. You are only going to apply the field so that the magnetic bubbles keep on moving close to the head, and then you read them. So everything is electronic. And remember, when you are having a mechanical, chances of failures are more. Something has gone wrong and the mechanical system falls. While in this, if everything is electronic, the chances of failure become very, very small. So that was one of the things which was very, very important for these things. However, if you want to have magnetic bubbles, there is a criteria that Hk upon 4 pi ms should be as large as possible. Definitely greater than 1. In my talks here, I have not introduced Hk, but in my notes you will find Hk, because I could not cover that particular portion of anisotropy. See, anisotropy can be represented by an equivalent field, and that's what's called anisotropy field. So this is anisotropy field which has the same dimension as 4 pi m. Okay, please refer to the notes which I have given, because I didn't have time to define this Hk, etc. In my first lecture note, you will find definition of Hk. First or second, I'm not sure, but Hk I have defined. It's generally by 2 K1 by ms. That's what happens, where K1 is an anisotropy constant. All right. So essentially, either you reduce 4 pi ms or increase Hk. I mean, many times we are saying that we want materials with larger 4 pi ms, but here we wanted a material with very small 4 pi ms. Many materials were tried. Some were orthoferrites, hexaferrites. Hexaferrites have a large uniaxial anisotropy, and people landed up into garnets. Garnets have very low magnetization. And they doped with this particular material with gadolinium, gallium, to make its 4 pi still smaller. And they use a substrate of what is called GGG, which is very expensive, unfortunately. Gadolinium, gallium, garnet. Know what about epitaxy? Epitaxy is essentially when a deposition of a single crystalline film on a substrate, on a crystalline substrate, where you expect atoms to just sit on the top of another atom below it. All right. So it's important that the lattice constant of substrate and lattice constant of the film that you are going to deposit should be as close to be equal as possible. You cannot make it 100% equal, but you would always like to make, otherwise at that particular point you will have stresses, and that's going to decrease the quality of the material. So epitaxial growth is always a single crystalline growth on a single crystalline substrate, where you're trying to deposit the material essentially atom by atom on the top of it. And one of the most expensive technique and one of the best technique for doing is this molecular beam epitaxy. If you are not very, very expensive technique, okay, where you can grow excellent quality material, and people have worked on monolayers, just deposit one single layer of material and high quality single crystal material. And by doing observation, you can really see that when one layer has been deposited. I think this pattern is called Reed pattern. I'm not. It's basically electron diffraction pattern. See, when the material is getting deposited by atom, the pattern gets sort of smeared out. Then one layer is completed, you get a nice pattern. You know that one layer has been deposited. Then again the second layer is getting deposited. Then again the diffraction pattern will go haywire. Then the second layer comes, and again you get clean. So you know now you have deposited second layer. Okay, it's a wonderful. It's very expensive machine. Okay, you can deposit layer by layer. But essentially, what epitaxy means that you are having atoms, and other atoms are coming and sitting on the top of these atoms. So if there is one particular atom here on the substrate, like this, other atom which you are trying to deposit comes and sits here. Another atom which comes and sits here. Now, if the lattice constants are not matching, it will not exactly sit here because you are forcing it to sit here. So there will be stresses there. Okay, which will try to alter the property, especially garnet is magnetostrictive and it changes the property. Okay, so it's important that you match the lattice constants of the substrate and the material that you are going to deposit as close to as much possible to be equal, as close to equal as possible. All right, that's why these gadolinium and gallium were deposited here to match the substrate lattice constant. All right, now wonderful materials were developed, but eventually it was found to be too expensive. And by that time, see, to make that quality films, substrate itself was very expensive. That has to be also very high quality. At the bulk rate was not found commercially feasible. And eventually, semiconductor memories took over. They became much cheaper, and around 80s or 85s, people lost interest in bubbles, and that field had a tragic end. Of course, not without developing a large amount of physics. I think it's only after magnetic bubble that we understood the domain walls much better, nail wall, block wall, various type of walls, how they affect the magnetic properties. All those things were understood thanks to bubbles. We could create a technology of developing almost defect-free films, cannot be 100% defect-free, with very low defect densities using epitaxy. It was all thanks to magnetic bubbles. It gave a lot of technological advancement, a lot of physics advancement, but eventually its application got lost. Yeah. Yeah.
Sir, when you deposit a layer on the substrate, so while depositing, so the surface may not be even. So somewhere it is more, somewhere it is less. So there will be a gaps.
That's right.
So how it leads to other properties?
No, the thing is that when you're talking of epitaxy, you have to make your substrate as clean as possible. See, these are the part of when you are depositing epitaxy. All right? It's true that 100% is impossible.
Yes.
Okay? To make 100% defect free is impossible. But the fact is that you have to make it as clean and as smooth as possible. Then only your epitaxy will work. In the case of semiconductor people, because they do a lot of epitaxy, so they have developed many of these technologies, how to make it really epitaxy successful. But the fact is that it has to be done. Okay, otherwise there will be defects. Okay, many times people don't care. I have seen people that, okay,
yeah, that is the question. Many people don't care, but
yeah.
Is there impacting of any other properties?
Yes.
That's
yeah,
why they
that's
are
what
not
I'm
caring.
saying. See, what I'm trying to say, if you are going to deposit a significantly thick film, then you don't care of what happens on one or two layers, where there are stresses. Okay? But if you are going to deposit ultra thin films, there was a time when a lot of people were working on mono layers. In fact, in one conference I go, when the person has, see, I am working on this particular study is on a 0.5 ml film. So I said, what is this ml? I had never heard this particular unit. He said monolayer, half monolayer. So I said, what do you mean by half monolayer? I can understand one monolayer, two monolayer. He says it means it's patchy film. So people were interested in, I mean, at a particular time they were interested in these type of materials. And actually it's a lot of interest in physics from the physics point of view, because you are creating a two-dimensional material. Of course, these days people talking graphene and things like that, which are two-dimensional material. But remember, these are old ages. You know, I'm talking 1980s. See, where to have a two-dimensional material was itself is a very, very important thing, because you know you are able to experimentally make a two-dimensional material and then test your theories which are developed for two-dimensional materials. Okay, so the fact is that if you are really going to make thick film, it doesn't matter so much. But if you are doing, then you have to take care of these things. You know. See, personally, I have never worked on epitaxy myself. See, when I worked on magnetic waves, the films were supplied to us by IBM at that time. My postdoc work was on that particular thing. So we never bothered to know how they deposited, but I know that I have visited their labs. It requires huge amount of technology to make them clean and make them put them in a proper epitaxial environment. Then, see, around the same time, a completely new area on magnetic thin film started getting developed. Which is the area of multilayers. Initially, this particular area got developed because suppose you are depositing a monolayer film, example I have given you, okay, you would like to measure its properties. But do you have an instrument sensitive enough if you want to measure magnetic moment of one layer of, let's say, iron? I'm just giving an example. Okay, do you have a sensitive enough material? And remember, it has to be on substrate, and substrate is going to be thick. Most of the signal is going to come from substrate. Even if you are going to put in squid magnetometer, okay, most of the is going to be either diamagnetic or paramagnetic. GG is paramagnetic. All right. Now, out of that tiny material which is there, how you determine? So people thought, why not we make multi-layers? Okay, you have one film, deposited film, very ultra thin film. Deposit another thin film on that particular thing of a different material which is non-magnetic. Okay, then deposit another film. Keep on doing, let's say, 100 times, so you'll get enough material. And in between, because there is a non-magnetic material, okay, so that's not likely to affect your magnetic moment. And then put it on your VSM or where you want it. The original idea, I remember, people talking about this particular thing. I was doing my postdoc at that time. Okay, why not we do it? Until they found that the properties, when you are making multi-layers, become quite different from single layer films. If you make, let's say, 20-layer film or 50-layer film, the properties become different. Why? For example, the material may diffuse inside the material. Okay, so the system is not complicated, but it leads to new degrees of freedom and new areas of work. And eventually, after GMR, that area really picked up. Okay, so let me just mention a little bit about multi-layers before I end my talk. So what we designate a multi-layer as TATB, N. It means you deposit a film of material A with thickness TA, and on the top of it, you deposit another material film, material B of thickness TB, and you deposit it N times. Okay, just I forgot to mention, in neutron mirrors, also this multi-layer was being used, because this can be used as a reflector to neutron beams. I'm not in that again in area, but I remember, see, when these multi-layers came, BRC people were very much interested of how to make these multi-layers so that they can be using as a neutron mirrors. All right, so you develop such type of multi-layers. It gives you a lot of freedom. You can try what is your A material, what is B material. Both A and B can be magnetic. One can be magnetic, another can be non-magnetic. Also, whether they diffuse, they don't diffuse. And there are three different terms which are coined. So let me just mention: super lattices, multi-layers, compositionally moderated film. If the materials diffuse quite easily between each other, then you cannot see sharp boundary between material A and material B. So a proper terminology will be compositionally moderated film. So composition gets modulated. So here you have, let's say, material A, you have here more of material A and less of material B. Then you have more of material B and less of material A. So it's a sort of a compositionally moderated film. There is no sharp boundaries because there is a lot of mixing of the material. If there is no mixing, you call it super lattices because then you are clean surface. So there is one particular lattice, there is another lattice on that. And in between you call multilayers. Multilayers is a generic term, it's a more generic term. And there are 2 or 3 applications immediately before spintronics came, were immediately looked. There was a very well-known paper of Freeman at that time, which actually was probably one of the reasons why this particular area became very interesting and a lot of people started working in it. He says that if you can really have a very thin film of iron, a 2-dimensional thin film of iron, the magnetic moment on iron will be 3.2 Bohr magneton instead of 2.2 that we are getting. That shows huge amount of interest because if you are able to do, you are going to get 4 pi mass, which is 50% higher than the normal thing. So people were immediately fascinated. This is for iron. Then chromium. Chromium is a very complicated material in a bulk form. It's generally referred as antiferromagnetic, but it's actually, there is spin density wave here. It's not really antiferromagnetic in that sense. It's a comparatively more complicated material as chromium. And Freeman's paper predicted that this will have Bohr magneton of 2.45. And it will become ferromagnetic. So interest picked up. None of these values, as far as I know, were experimentally tested. They were never found. Maybe people were not able to perform the experiments, or maybe the theoretical prediction was not correct. We never saw that type of magnetic moment in iron and chromium, but you know, that was the area which sort of gave a huge momentum to the area of multilayers. Second area, about which I have briefly mentioned in my first lecture, is that when I am creating multilayers at the surface, at the interface rather, there is going to be some sort of anisotropy because suddenly you find a departure from the normal environment. A particular atom inside a film will have a different environment, but an atom at the surface will have a different environment because at one side there is no atoms or atom of different type. All right? So this also acts essentially as a surface anisotropy, and this surface anisotropy can be used to modulate your normal anisotropy and make a film and sort of play with your anisotropy of the material. And this is an expression which people found. I will explain to you. This expression is also given in your quiz book. If you prepare a multilayer where thickness of your magnetic layer is T and the surface anisotropy is Ks, okay. You do not know how to measure it exactly in that sense, but you know, we'll see that about that later. And Kv is the volume anisotropy about which we know, because you know that particular material and you know what type of anisotropy it has, you know it's what is its constant. You can put it in a torque magnetometer and you know what is the bulk anisotropy of the material. Now, overall anisotropy of the material would be equal to Kv plus 2Ks by T. Generally for uniaxial system, because uniaxial systems where much more in use when we are talking about anisotropy. People are generally anyway using uniaxial system because they have large anisotropy. So, if you are going to very small t, you will be able to make overall film much more anisotropic. You can increase the anisotropy, and therefore you can change your loop. I have told you that anisotropy is one thing on which you can change the loop. Okay? So, a large number of people developed using this idea an anisotropic material where originally the material did not have that type of anisotropy. But just by making a multi-layer, we used surface anisotropy to enhance the anisotropy of our system. This is another use for which people were using. The third thing about which I will talk about is, of course, the famous experiment by TIFRH and group, of course, also by Grunberg, I must not forget, is about giant magnetoresistance. It depends on how the films, magnetic films in a multi-layer couple to each other. I'll probably, if I have time, in my next talk, I will give you some FMR data on the coupling of two layers with a non-magnetic layer in between. So you have a film here, which is magnetic, and then you have non-magnetic, and then you have magnetic. Whether there could be coupling between this and this. The basic idea on which actually TIFRH and initially Campbell were working for a long time, there had been a very large number of papers on what they used to call as a two-current model, which people were reading, and I don't think a very great number of people were interested in them. Essentially telling that when you are talking of current, which essentially is carried by electrons, electrons also have spins. So we should divide the current into a spin up and spin down current separately. And a large number of papers before anything of spintronics was known. There, TIFRH and Campbell were actually talking about these things. And as the story goes on in France, that Babbage, who was the first author of the paper of GMR, which got Nobel Prize, he was a postdoc in TIFRH's lab. He's a Brazilian. So they were working on multi-layers. So that fellow says, can't I just do magnetoresistance on them? And TIFRH told, okay, if you want to do magnetoresistance. And he did magnetoresistance, suddenly found a huge value. Then for TIFRH, it was very easy to explain, okay, it's just two current model that he was talking about. There is spin up and spin down current being scattered separately. Led to huge discovery, changed the entire area of electronics, just that one measurement. I don't know about the Grunberg's measurement, but Campbell's measurement, TIFRH's measurement, I know about this. That's what the story is, that he just said that I want to measure magnetic, okay, go and measure magnetoresistance, what's wrong? All right, what happens? If you assume that it depends on the scattering depends on the direction of the magnetization. So if you have this particular layer which is magnetized like this, another layer which is magnetized like this, then there is a chance of equal scattering of spin up and spin down currents from both the layers. But if I flip by applying magnetic field or by doing whatever, so that they become parallel, then one of the currents will get shorted and the resistivity will drop. That's the basic simple idea. All right. Only problem is that in the case of TIFRH, etc., this high value of magnetoresistance was observed for a very large magnetic field and at very low temperature. And that type of fields and that type of temperature you cannot put in device. If you want to have we give you a recording media or recording head and say that you put in liquid helium temperature, then only it will work. I don't think anybody is going to buy. Liquid helium itself is not very easy, it's fairly expensive. You want everything at room temperature and at the fields that you are going to produce in this particular head. Magnetoresistive heads were common in those days, and they were using permalloy, it's alloy of iron and nickel, for recording head. we showed a maximum magnetoresistance of 2%. You know what is magnetoresistance? There is a resistance, you apply a magnetic field, resistivity changes. That's what's called magnetoresistance. All right? On the application of magnetic field, resistance changes. And that's what we were doing, that if there is a bit which has to be read here, your head sees the magnetation, and because of this, the resistivity changes. And this change of resistivity is monitored, and then you know that you have read a bit. If there is no change in magnetization, then the resistivity will not change. So that's the way reading is done in a device. Now, what Parkin did, he was in IBM at that time. Actually, he did not get Nobel Prize. He used the idea of this FERT and FERT. He said, I don't care about multi-layers. For me, 3 layers are enough. All right? But if I am able to raise from 2% to 4% or 5%, for an industry person, it's a huge change. I don't care about 50%, 60%. See, that's the difference in which an industry person will look and a physicist will look. A physicist is excited, I have got 50%. Industry, no, I don't care. I want something which works for my device. For my device, from 2%, if I am able to make it 4%, that itself is a very big discovery for me. But I must get this 4% at room temperature and at the field which I am going to get in my device. The field which is going to be created by media. Of course, these days the difference between head and the media is extremely small. They are essentially almost, you will not say touching, but very, very close. And you have to go too close, because if you are writing smaller bits, the field is going to be very, very small until you go very close to this thing, that particular medium. So that itself is a technology, how to go that close, how the head goes so close to the media and reads. Otherwise, the field will decay as 1 upon r square. And that's what it's technology about. All right? So he developed first what we call as a spin wall. I'm using another set of notes. According to the published data, the original spin wall had the following composition. There are always certain things which are not published. These are technological things. If you are going to use that, you are never going to get that result. I mean, many of my former PhD students are in industry, and they always told me that actual composition will never be revealed in any research paper. So they will say this particular material, they will give approximate composition. So if somebody wants to copy them, you can keep on copying, you will never get that result. Because there is something which is there, which is hidden. In fact, I have gone to the industry with some of those things. They will write some material with X this much. X, sorry, I do not know what is X. Okay, they will not tell you. That's the economics, okay. So this is permalloy nickel iron, 50 nanometers. Then copper, 2.6 nanometer. Again, nickel iron permalloy, 50 nanometer. And iron manganese, which is 10 nanometer. Four layers. The two magnetic layers that I am talking are these two. Closer to the one layer is iron manganese, which is sort of antiferromagnetic material and creates an anisotropy which holds the magnetic moment, effectively increases the coercivity of this particular layer. So when I apply field, the other layer will switch, but not this. See, if I want to switch only one of the layers, and if both of them are of the same material, if I apply a field, both will switch together. You don't want to switch, because I want it to be either parallel or anti-parallel. So I want only one of them to switch. So if I must hold this particular thing by increasing its coercivity. Okay? So this coercivity is artificially enhanced by putting iron manganese, sorry. Wonderful ideas. Okay? physicist, you can appreciate, the way technologies think. And he developed first spin ball. And I had visited Fujitsu at that particular time, and he showed me a beautiful curve, how magnetic recording with years, the density is increasing, and the curve shows like this, like this. And he said, here is a spin ball. Changed the recording density dramatically, because you could read much smaller bits. After that, the entire area where you are looking currents as a combination of spin up and spin down current developed. We have now a full-fledged area of spintronics. We had electrical engineering, we went to electronics, we went to microelectronics, we went to nanoelectronics, we are now talking spintronics. And it has blasted like anything. There are so many things, I cannot keep track of it. Okay. So I will not be able to tell you about that particular thing, but I thought I just gave you a brief idea of how magnetic materials developed over at least my lifetime. I think, thank you. Any questions? You are most welcome. Yeah.
So many people quoting that if they get a crystallite size 200 nanometer or 300 nanometer, they are saying that still their particles are nanometers. So what is the ideal range of nanometers actually? So
What
we get 50 nanometers.
What you will call nanometer, that's what you are calling. What we will call as a nano material.
Yes.
Is that your question?
Yes. Actual range of crystallite size also.
Okay. See.
So some people saying 50, 100, 200, 300 also. And that is nearly equal to micro.
I am trying to answer your thing. See, if you want to sell something of yours, you have to make it attractive. Agreed? All right. So everyone will like to call whatever you are making as nano, because nano is sales. Nano is fashionable. All right. But generally accepted terminology is that anything which is below 100 nanometers, we will call nano. It's a sort of generally accepted thing. But even 100 nanometer for many of the things is not really nano. We'll prefer to call 20 nanometers, 30 nanometers as nano. We don't generally get 1 nanometer, 2 nanometer, because these are, this is different range, where particle sizes are extremely small. And you may not have, at least in magnetic material area, they are may not be of that much interest. Let me try to answer the same question in a slightly different fashion. See, you have certain things which you call as a property of a thin film, which are closer to the bulk material. So as you increase the thickness and you start finding out that your properties are saturating more towards bulk value, you are out of the nano region. See, so long your properties are significantly different from the bulk properties, okay, I will still like to call it nanometer even if the size is 100 or 150 nanometer. That's the first reason. But the fact is that, as I said, if you go by the fact of the matter, if you could call it nano, everyone will call it nano, because nano sells. Okay, thank you very much. My email is with you. Of course, I have one more lecture in the afternoon. So in case you have any questions or any doubts, feel free to write.